all about practicing with our new integration techniques. We want to be able to find antiderivatives of complex functions. So the strategy guide for integration is at the beginning of this packet, and parts of the guide are reprinted for us to go over. We only have a few specific formulas for antiderivatives. So they're all listed here. These are all the antiderivatives you know. So if something doesn't look exactly like one of these formulas, you have to apply another technique to sort of make it look like this before you can take an antiderivative. So you'll have to use one or more of the following techniques. You want to look at whether you see a sum or a difference. If you see a constant multiple of a function you know how to integrate. You can always algebraically manipulate the integrand. So that's like, we've done some like this where you square the numerator and then maybe you divide every term by the denominator. There's U substitution. The thing you want to look for is you want all of your x's to cancel, right? So you would look for, does both of a function and its derivative appear in the integrand? By parts, whenever you have a product, that's often a good hint that you might use by parts, but only if you can't use U substitution. U substitution is easier, but if U substitution doesn't work, then by parts is a good next option. And then partial fractions. So this is really a special case of the algebraic manipulation of the integrand. Okay, it breaks a fraction with a factorable denominator into the sum of simpler fractions. Okay, so in general, integrals are harder than derivatives. But there's a silver lining in that you can always check your answer, because once you find what you think is the antiderivative, you can take its derivative and make sure you get the original integrand back. So you can always check, and you'll know if you got the answer right. All right, so I'm not going to do all of these integrals with you. We're just going to try to discuss what techniques we might try on each of these integrals. So if I have the integral of x times e to the x squared, I notice that it's a product, right? But I'm not going to jump to by parts because I also notice that an x squared appears in the integrand, and so does its derivative x. So I would start by trying U substitution. I would let U be x squared and try a U sub. I'm not going to go through the whole thing. Excuse me. All right, but this next one, it looks very similar to the first one, but instead of x e to the x squared, it's just x e to the x. So it's a product, and U substitution won't work this time because if I just let U equal x, all I'm doing is changing the name of the variable. So it's not helpful at all to choose a U here in the way that I chose it last time. Right? So last time I let U be the exponent on E. If I do that here, I get nowhere. So this one I would do by parts. I would let U choose a U and a dv. dv being the more complicated thing as long as you can still integrate it. So e to the x dx will be my dv, and my U will be my x. So that one I would do by parts. So this U sub by parts. And we don't have to go through the whole problems. The goal of today is to be able to look at an integral and pick a technique that we think will work. You can't always be 100% sure, like in this next example. I have two ideas when I look at this integral. My first idea is that, oh, I see an x cubed and an x squared in the integrand, right? So my first idea might be to try U substitution, right? But then if that doesn't work, another thing I might notice is that the denominator is factorable. So I could rewrite my integrand as 2x squared plus 4x minus 9 over x times x squared plus 9. And when you write it like that, what technique suggests itself? Partial fractions, yeah. So I'm not going to tell you which one works, right? But you would just try one. If it doesn't work, try the other. That's what makes integrating harder than differentiating, right? There, you have ideas what might work. You try something. If it doesn't work, you try something else. There's no like hard and fast way to know what technique will work. All right, so for this last one, D, you should notice that the integrand can be simplified. So I could square out the integrand, and I would get x squared minus 2x plus 1 all over x dx. And then I can unadd these fractions, right? So this becomes the integral of x squared over x minus 2x over x plus 1 over x dx. Because now they all have the same denominator, so when you add fractions that have a common denominator, you would just add the numerators, and you'd get back to where we started. And then just simplify. So this becomes x minus 2 plus 1 over x dx, and now it's a straightforward integration. So those are our 4 main techniques: U sub, by parts, partial fractions, and algebraically simplify the integrand.